Hello to everyone. Today we'll continue doing laboratory work number 5, and today we need to answer all three next questions according to laboratory work number 5. First of all, we need to test the significance of regression model by using f-test. Then we need to verify the presence of autocorrelation, and then we need to make prediction of a dependent variable y. But before we start, continue our work, I wanted we return to our outputs, because if you remember, on our previous video instruction, we began from replacement our outputs by sorting them in ascending order by settings by our dependent variable y to do first step of verification the presence of heteroscedisticity, and that's why we need to return to our outputs by using our outputs from our primary table from this kind. Good. So you can see that some of our calculations, which is based on using verification of heteroscedisticity, will change, so it doesn't matter. We will use the previous information according to this kind of methods, but if we want to continue our work, we need to use our primary outputs. So, okay, now we can start doing the first step in testing of significance of our regression model. So if you remember, we created regression model, and our regression model has such coefficient of regressions. This is our two variable model between our income and savings, and we also use for this reason these formulas, or we also can use another symbols to probably to better reminding how we can calculate f-test by using SSR divided by SSE, because SSR, it is our differences between estimated value of y and mean value of y, and all these values, if you remember, lie on our regression line. And we divide on SSE, so it is sum of square of our errors, because differences between our actual value of y and our estimated value we can call like errors, unobserved factors, or residuals. And then we corrected all this dispersion by degrees of freedom. So the first of all, we need to fill all this table, and first kind of indicator, it is our estimated value of y, which we can calculate it by using our coefficient of regression, by using the first one, a0 plus a1, and multiply by x, and x we take from our outputs. Don't forget to fix it our coefficient regression to extend all our values of estimated y. Then we need to define first our differences between estimated value and mean value. Mean value I calculated before, so it is very easy way to define mean value of y by using a function Excel heteroscedisticity. And we again should fix our mean value to extend all our 18th value of these differences. Then we take this kind of differences to the power of 2 to the second power, and then we need also to define the sum of these squared differences. Then we need to define another kind of differences, our SSE or residuals. It is differences between our actual value of y and estimated value of y. And then we need to also take to the power to the second power these differences and find the sum of all these differences. And now we can again remember that K1 it is our number of independent variable which included into our model. We have only one x, and that's why K1 is equal x, and K2 is equal 18 minus 1 or minus K1 and minus 1. So it's equal 16. And now we just put it into our formulas by using first proportion, first numerator. It is our y estimated minus mean value divided by K1, and we need to take round brackets, and then we need to divide this numerator by denominator, and by using again round brackets divided this sum by 16. Good. So to make some conclusion according to our significance by using f-test, we need to find also table value of f, and probably you remember that for this reason we need to use f-raspolver in Excel, where we should write the level of probability. Then we need to define first order degrees is equal 1 and second order degrees which is equal 16. So we have very interesting situation which can prove the theoretical hypothesis about that about the existence or presenting into our regression model heteroscedisticity. So if you remember, I said about these features on our previous video instructions. And I said that when we have heteroscedisticity into our model, our F and T statistics give us incorrect information. They are overestimated. And we can see it on this example because we have a heteroscedisticity. We see that we make such conclusions by using M criteria, but by using our OLS method, still based on testing of significance and using for this reason f-test, we can see that this test show us that we have a good model, we have good significance of our model, and it gives us not true information, overestimated information about using our regression model. And you know that in case of presenting heteroscedisticity, we need to change our methods of calculation, our estimators, so our regression coefficients. We need to use not OLS but GLS, generalized least square method. Next, our question in this laboratory work is autocorrelation. And before we start doing and testing this kind of problems in regression analysis, we need to talk about some important moments. So first moment, when we talk about autocorrelation, we talk about correlation between only residuals. It's very important, and you do not forget about. And probably you can see that we have some table, and in this table we use only u. U, this is our unobserved factors, it is our residuals, so we only talk about correlation between residuals when we talk about autocorrelation. So when we talk just about correlation, we can talk about x's, can talk about x and y, but when we talk about autocorrelation, according to regression analysis, we talk only about correlation or connection between residuals. This is first moment. The second moment, when we talk about autocorrelation, we talk, and you should know about this, that when we talk about of correlation, we talk in most cases only about time series data. Time series data, it is our data set that we take in chronological ordering of observations. So that's why in this laboratory work we have not observations, but we have another name of observation. We have periods of time. So this is kind of time series data. And that's why when we talk about connection between residuals, we talk about connection, for example, between residuals from second periods with first periods of time. We talk about residuals between connection. We talk about connection between residuals from third period of time with residuals from second periods of time. It's very important. So that's why if you look at this kind of differences, you can see that we have some delay, or in other words, we have some lagged differences. Lag, it is has a meaning of delay of something in time. So we have only one such delay. So we compare some kind of residuals with the previous period of time with log, which is equal 1. So in other words, you can find that in some places of guidelines for laboratory work, or some places of my presentation to topic 5, I write or I call such kind of connection with delay which is equal 1, like first order after correlation. First order after correlation. So, if, for example, if we want to compare our residual from first period of time, we can define these differences for this kind of period, because we do not know what kind of residuals we have before our first period. So we can start for example, calculating this kind of differences only with the second period of time. And for this reason, you can see the formulas where you should to calculate the numerator, and you can see that are some of these differences starting not from I is equal 1, but from I is equal 2. So that's why we can never start from first position. We always will start from the second position for first order after correlation. And the third important moment, it is understanding and remembering that the effects of presenting autocorrelation is the same like presenting of heteroscedisticity into regression model. It means that the most important negative effect is that our OLS estimators are not blue. They are still best, linear, and unbiased, but they are not effective. So to make good conclusions, we can use our regression model, which we created by using OLS method. We need to change our OLS method and use for this reason GLS. And how to do it, you can read, and I recommend you to read into my presentation to topic 5. And now we can start verify the presence of autocorrelation using the Darbin-Watson criteria. For this reason, we use this kind of formulas. It's very simple way which can allow us to understand if our model has autocorrelation between residuals or not. So first of all, we need to define these differences. These differences we can take from our previous calculation when we are using f-test. So our y actual value of y minus estimated value y, it is our this kind of differences, and we need to use the same it into the square. So we have these two columns, and just we need to also find the sum of our sum of squares of residuals, which is equal 0.57. Next, it is we need to define our numerator of Darbin-Watson criteria, and for this reason we need to use what kind of differences between residuals, and we take it from this kind of columns. So we need to define, and we're starting from the second periods of time. So first, our differences between between second and first, we can define by this kind of calculation, and we can do this the same for all our periods of time. And then we need to take again these differences into the square to the power of 2, define also the sum of these differences, and then we need to divide the last one by this one. So we have the estimated value of Darbin-Watson criterion, which is equal 0.95, and then we need to find also our again number of independent variable. It is equal 1. Then we need to define the number of observation. It is equal of 18 periods of time. For what reason we need to define it? To find table value of Darbin-Watson criteria. And to find table value according to our independent variable and number of observation, we need to use table information from, for example, this kind of site where I find this table with probability of 0.05, and according to K it is our M is equal 1, and such the L and the U. So the L it is 1.16, and the U it is 1.05. 1.39. And how we can make conclusion? We can make conclusion by using this kind of graph from my presentation about topic number 5 about autocorrelation. On this graphic we can see the different zones, and also you can see that the limit of table value of Darbin-Watson criteria lie between 0 and 4. We have the middle, which is equal to, we have our the L, the U, and from another side 4 minus the U and 4 minus the L. So we have that between this kind of zones, so which is concentrated around the middle place, middle point of this limits between the U and 4 minus the U. We can say that there is no positive or negative autocorrelation because we have some null hypothesis. So the null hypothesis, it is no positive autocorrelation and no negative autocorrelation. And in this limits, we can not reject this null hypothesis, and it means that we haven't autocorrelation. It is good. But for example, we have two zones where we can detect presenting autocorrelation. So the first zone, it is presented positive autocorrelation. It is between 0 and the L. And the second zone, it is between 4 minus the L and 4, where we have negative autocorrelation. And this Darbin-Watson criteria have two zones where it can explain if we have or not have, doesn't have autocorrelation. It is between the L and the U, and 4 minus the U and 4 minus the L. So now we can analyze in what kind of zones we can put our estimated value of Darbin-Watson criteria, 0, 95. For this reason, we can also calculate the differences between 4 and the L, or first of all, the U, and 4 and the L. So we can be sure that our estimated value of D, 0.95, is presenting in the first R zone between 0 and the N, between 0 and 1.16, and that's why we can say that we have in our regression model positive autocorrelation, positive autocorrelation between our residuals. So this is our conclusion. We can write positive autocorrelation, but you can be careful when you will change the number of your individual when you change your individual number and, for example, put, for example, I don't know, 12. So it why it doesn't change? Okay, I can show you because I used into this table not formulas but values, digitals for all these yellow spaces. So I want to recommend you to be aware about changing your individual variance, because this kind of criteria will be changed, and of course it can be existing in different kind of zones, not only in this zone but in any kind of these zones for table value of Darbin-Watson criteria. So be careful when you make a conclusion. Okay, and the last our task in our laboratory work number 5 is to make prediction, and we can technically do it very simply way by using RA0, by using RA1, and by using for prediction dependent variable if our amount of income, so our predicted value of x, is equal 28. So in this case we can calculate that our prediction value of dependent variable y will equal 2.23. So, but if we make conclusion from all our calculation, we can say that our or OLS estimators are not blue, so they are not effective, and that's why our regression model we can use to make good prediction and to make a good managerial decision, because we have and heteroscedisticity and autocorrelation. That's why this kind of prediction are not reliable. So it is the end of our laboratory work number 5. Bye bye.